Okay, in this section of the lab, we are going to be trying to keep the sum of the forces equal to 0.98, which would mean that the difference between our two masses is going to be 100 kilograms. So to start off, I'm going to start off with a 200 gram, I think I said kilograms a second ago, I meant 100 grams. So I have a 200 gram and a 100 gram that I'm going to be letting go through the Atwood machine. I have to tell you, this 200 gram, I'm afraid it's going to go flying, but we'll see what it does. I also have my Logger Pro set up over here, so I'm going to be using that, and then I'll show you a screenshot of it in between. I had to stop it because I felt like it was too much. All right, I do have a good screenshot, and I'll show that to you in just a second. Here's a screenshot of Logger Pro. You can see that the slope is 3.045, which is the acceleration. Okay, now I'm going to add 50 onto each side, which seems like, I don't know, it seems like a little bit counterintuitive, like you're adding so much mass that ought to make it go even more wild. However, we're hoping to see it slow down. And again, think in terms of a freight train. If this is a freight train, you know, how fast would it be going? All right, I need to get my Logger Pro started. I don't know if you can tell if it's slow or not, but let's hope. Okay, amazingly it was slower. I'm going to take a screenshot of that for us. Here's the screenshot of Logger Pro for the second one. The acceleration is 2.286. Okay, I have added 20 onto each side. I was going to hold these up and show them to you, but I'm not sure if that's, I'm not going to. Hopefully you can sort of see it, like on black pencil. Okay, so there's my 170, and then over here, I have 270, so where's my 270? All right, so my Logger Pro setup. They hit each other on the way, but I think I have enough data in Logger Pro. Let me see. Yeah, I do. I've got enough data, and it looks like a good one. Here's the third screenshot. The acceleration is 2.050. Okay, last trial. This time we have a 200 gram and a 300 gram. So we're going to send those. And again, it seems like they are so heavy, something dangerous could happen, but my hope is it's actually slower. We'll see if we can, if that's a visible difference, I'm not sure. So I'm going to set my logger, and here we go. Actually, it was kind of controlled, right? My logger looks like a small amount of data, but I think it'll work. Let's see. Oh yeah, again, pretty good. I'll do a screenshot. All right, the last trial is 1.815 meters per second squared. Okay, so that's the end of our tables that we need to do. I want to show you one more thing, and I'm trying to decide like how big of a math should we do? Because there's a question on the next page that asks, is there a situation where there is zero acceleration? Okay, what would the situation be where there is zero acceleration? When we were doing this the other day, I actually alluded to it. In other words, if zero acceleration means constant velocity, how could we create a situation where there's constant velocity? Well, if there's constant velocity, zero acceleration, that means the sum of the forces must be zero. That means the difference between the two sides must be zero. That means that both sides are the same. So let's test that out. And I think the biggest that I have matching with each other are the 200s. I'm just going to do a 200 on each side. And I don't know, I just think this is so cool to see. I guess just because it literally is perfection. It's not often when you see perfection, especially when you're trying to do things in physics that don't always work out the way you want them to, but this one does. This one's pretty cool. So I had this situation set up actually again the other day before we started, and I had it in an equilibrium. Trying to get it on the so can you see this? They're spinning. This string is, they always spin on this string. So, but they're the same mass, right? So they're just sitting here. Now if I change the lengths, they should still just sit there. And they do. They're just suspended, right? No velocity and no acceleration. All right, could I create a situation where there is a constant velocity? So again, I personally think this is pretty cool. Here they are. I don't know if you can see all the way to the very bottom. I don't think you can. One of them is, it's not on the floor, it's just barely above the floor. I've manipulated it so that it's just barely above the floor. This one obviously is hanging here. They're just hanging in equilibrium. If I just give this one a little tap, you should be able to see constant velocity. Oh, I need to tap it harder. There was too much friction in the system. I'm going to give it a little bit more of a tap than that. Okay, but isn't that cool? It's just a constant velocity. I mean, obviously, again, it did slow down a little bit. I should give it more of a yank like that. Let me try to give it more of a yank so you can see it. I just think it's cool because it's constant. Right? I mean, it's not completely constant because we did see some friction, but do you notice how it just glides? Like, I don't know. If you were touching it, maybe you'd think it's as cool as I do. Maybe not, because I just get into that kind of thing. But I just think it's pretty cool that it's just such a constant velocity. If I added any more mass onto either side, as we have seen, it wouldn't be that way. It would be accelerating, and it just gets out of control really quickly, right? Okay, that's the end of that. We will work on compiling this data.